Tonight, we are going to talk about something so powerful that it can outshine entire galaxies, something so distant that its light began traveling toward us before Earth even existed, and something so violent that it reshaped the early universe itself. These objects are called quasars. They look like tiny points of light in telescopes, but that appearance is misleading. A quasar is not a star. It is not a galaxy. It is the blazing heart of a galaxy being torn apart from the inside. Quasars are powered by black holes, but they shine brighter than trillions of stars combined. They are the most energetic, most extreme, steady objects the universe has ever produced. And understanding quasars means understanding how galaxies were born, how black holes grow, and how the universe evolved from darkness into light. To understand why quasars are so bright, you have to forget how stars produce light. Stars shine because nuclear fusion releases energy in their cores. That process is powerful, but it is inefficient compared to gravity. A quasar does not rely on fusion at all. It relies on gravity doing what gravity does best, pulling matter inward and converting motion into energy. When matter falls toward a supermassive black hole, it does not drop straight in like water into a drain. Instead, it spirals. It forms a vast spinning structure called an accretion disk, and inside that disk, physics enters an extreme regime. As gas clouds fall toward the black hole, they accelerate to incredible speeds. Friction between particles heats the disk to temperatures hotter than the surface of stars. At these temperatures, atoms are torn apart. Electrons are stripped from nuclei. Matter becomes plasma. Magnetic fields become twisted and amplified by the spinning motion. These fields snap, reconnect, and fling particles outward with enormous force. Every second, energy pours out in the form of light, X-rays, ultraviolet radiation, and powerful particle jets. This process converts mass into energy with an efficiency far greater than fusion. A quasar can convert up to 10% of the infalling matter directly into radiation. By comparison, nuclear fusion converts less than 1%. This is why a quasar can outshine an entire galaxy. Billions of stars burning for billions of years cannot match the raw power released by matter falling into a black hole over a much shorter time. The black hole itself remains dark, hidden behind its event horizon, but the region just outside becomes one of the brightest places in the universe. The light doesn't come from the center, it comes from the final moments before matter is lost forever. In that sense, a quasar is powered by destruction. It is the universe extracting energy from matter at the edge of annihilation. The rotation of the black hole plays a crucial role. A spinning black hole drags space itself around with it, a phenomenon known as frame dragging. This twisting of space intensifies magnetic fields and allows even more energy to be extracted from the system. In some cases, energy is pulled directly from the black hole's rotation and launched outward as narrow, focused jets. These jets travel at nearly the speed of light and can extend for millions of light years. They punch through the surrounding galaxy and blast into intergalactic space, carrying enormous amounts of energy far beyond the quasar's host. These jets are not side effects. They are central to how quasars shape the universe. As they travel, they heat surrounding gas, disrupt star formation, and redistribute matter across vast distances. Entire regions of space can be altered by a single quasar. In the early universe, where galaxies were closer together, this influence was even stronger. Quasars acted like cosmic engines, injecting energy into the surrounding environment and preventing gas from cooling too quickly. This helped regulate the growth of galaxies and may explain why many galaxies stopped forming stars when they did. Yet, despite their power, quasars are surprisingly small compared to what they affect. The region generating the light may be no larger than our solar system, yet its influence reaches across millions of light years. This mismatch between size and impact is one of the defining features of quasars. They prove that gravity, when combined with motion and magnetic fields, can outperform any other energy source in the universe. Another remarkable feature of quasars is their variability. Their brightness can change over days, weeks, or months. This tells us something important. If an object changes brightness quickly, it must be small. Light cannot vary faster than it can cross the emitting region. These rapid fluctuations revealed early on that quasars were compact, not spread across entire galaxies. This was one of the clues that led scientists to realize quasars were powered by black holes rather than stars. The universe was revealing its secrets through timing as much as through light. Quasars also emit across the entire electromagnetic spectrum. Radio waves, infrared light, visible light, ultraviolet radiation, X-rays, and gamma rays all pour out from these systems. Each wavelength tells a different part of the story. Radio waves trace the jets. Infrared light reveals dust heated by radiation. Visible and ultraviolet light come from the accretion disk. X-rays probe the innermost regions where gravity is strongest. By combining these signals, astronomers can reconstruct the structure of the quasar in extraordinary detail, even from billions of light years away. What makes quasars even more important is that they mark a specific era in cosmic history. The universe was not always filled with quasars. They were far more common when the universe was young. Over time, as galaxies matured and gas supplies dwindled, quasar activity declined. Today, quasars are rare. Most supermassive black holes are quiet, including the one at the center of the Milky Way. This tells us that quasars are a phase, not a permanent state. They represent a violent adolescence in the life of a galaxy. That realization changes how we see the universe. The calm galaxies we observe today were once chaotic, energetic, and dangerous. Their cores blazed with quasar light, reshaping their surroundings. The universe we inhabit is the cooled-down result of that earlier violence. Quasars were not anomalies. They were a natural stage in cosmic evolution. Even now, quasars continue to teach us new things. Some quasars appear to challenge our understanding of how quickly black holes can grow. Others show unexpected patterns in their emission. Some seem to flicker on and off in ways we do not yet fully understand. Each observation pushes astrophysics forward, forcing revisions to our models of gravity, accretion, and cosmic structure. Quasars are reminders that the universe builds complexity through extremes. It creates objects so powerful that they reshape entire galaxies. Yet those objects arise from simple principles: gravity, motion, and energy. There is no exotic force required, just mass falling inward and space bending around it. In that sense, quasars are gravity made visible. They are the universe showing us what happens when gravity is allowed to operate without restraint. They are not just bright lights in the distance. They are windows into the deepest processes shaping the cosmos. To understand the true importance of quasars, you have to place them inside the story of the early universe. The universe was once a very different place. It was smaller, denser, and filled with vast amounts of raw material. Gas had not yet settled into the calm structures we see today. Galaxies were forming rapidly, colliding, merging, and tearing each other apart. In this chaotic environment, quasars were not rare exceptions. They were common. They were a defining feature of the universe's youth. When we look far enough into space, we are not just looking far away. We are looking back in time, into an era when quasars dominated cosmic light. During this early period, galaxies contained enormous reservoirs of cold gas. Gravity pulled this gas inward, feeding the central black holes at extraordinary rates. Unlike today, where most galaxies have exhausted or stabilized their gas supplies, early galaxies were overflowing. This allowed black holes to grow with incredible speed. Some reached billions of solar masses in less than 1 billion years. This rapid growth is one of the greatest mysteries in modern astrophysics. According to simple models, black holes should not grow that fast. And yet quasars prove that they did. Something about the early universe allowed gravity to work with brutal efficiency. As quasars ignited, their influence spread far beyond their host galaxies. The energy they released did not remain confined to the core. Radiation streamed outward, heating gas across interstellar and intergalactic space. Powerful winds and jets pushed material away from the center, sometimes at thousands of kilometers per second. This process changed how galaxies evolved. Gas that might have formed new stars was instead blown out or heated to temperatures too high for collapse. In many galaxies, quasar activity effectively shut down star formation, locking those galaxies into a quieter future. This process, known as feedback, is now understood as one of the key mechanisms that shaped the modern universe. Without quasar feedback, galaxies would look very different today. They would be larger, denser, and filled with more stars. The balance between gravity pulling material inward and quasar energy pushing it outward created the variety of galaxy shapes we see now. Spiral galaxies, elliptical galaxies, and massive galaxy clusters all bear the imprint of past quasar activity. Even the Milky Way, which appears calm and stable today, likely went through an active quasar phase billions of years ago. The quiet center of our galaxy is the aftermath of that earlier violence. Quasars also played a major role in changing the state of the universe itself. In its earliest stages, much of the universe was filled with neutral hydrogen gas that absorbed light. As quasars and early stars formed, their radiation began to strip electrons from this hydrogen, turning it into ionized plasma. This process, called rionization, transformed the universe from a dark, opaque place into one that allowed light to travel freely. Quasars were among the most powerful contributors to this transformation. Their intense ultraviolet radiation reached far into space, clearing cosmic fog and making the universe transparent. In this way, quasars helped turn the universe into something we could eventually observe. Without them, much of the cosmos would remain hidden behind walls of gas. Every distant galaxy we see today owes something to the early quasar era, when light first carved pathways through space. Quasars did not just shine, they prepared the universe for visibility. Another remarkable role of quasars is how they help us map the universe. As quasar light travels toward Earth, it passes through countless clouds of gas. Each cloud absorbs specific wavelengths, leaving tiny fingerprints in the quasar's spectrum. By studying these absorption patterns, astronomers can detect matter that emits no light of its own. This technique allows scientists to trace the distribution of gas, measure chemical abundances, and study the structure of the cosmic web. Quasars act like backlights, illuminating the invisible scaffolding of the universe. These observations reveal that matter in the universe is not spread evenly. It forms filaments, clusters, and vast empty voids. Quasar light shows us where gas is dense and where it is sparse. It reveals how elements heavier than hydrogen spread over time, forged in stars, and carried outward by winds and explosions. In this way, quasars become tools for cosmic archaeology. They allow us to reconstruct the history of matter across billions of years. The relationship between quasars and their host galaxies is deeply interconnected. The mass of a galaxy's central black hole is closely linked to the mass of the galaxy's central bulge. This suggests that black hole growth and galaxy growth are tightly coupled. Quasars are the visible phase of that coupling. When a quasar shines, it signals a moment when the black hole and galaxy are evolving together in a dramatic way. Understanding this relationship has become one of the central goals of modern astronomy. Yet quasars also show us the limits of growth. Eventually, quasar activity declines. The black hole consumes or expels the surrounding gas. The fuel runs out. The quasar fades. What remains is a massive black hole sitting quietly at the center of a mature galaxy. This transition marks the end of an era. The universe moves from a violent, energetic youth into a calmer, structured adulthood. Quasars are the beacons of that transition. Despite decades of study, quasars still surprise us. Some appear brighter than expected. Some flicker unpredictably. Some show evidence of extreme winds moving at a significant fraction of the speed of light. Others appear in unexpected environments. Each discovery forces scientists to refine their models. Quasars remind us that even when we think we understand something, the universe still has more to teach us. At their core, quasars represent the universe at its most intense. They show what happens when gravity is given vast amounts of fuel and little restraint. They turn invisible black holes into the brightest objects ever seen. They reshape galaxies, alter cosmic structure, and illuminate the deepest reaches of space. They are not side effects of cosmic evolution. They are drivers of it. When we study quasars, we are studying the universe learning how to organize itself. We are watching gravity sculpt matter, energy regulate growth, and light carve order out of chaos. Quasars are not just distant lights from the past. They are fundamental chapters in the story of how the universe became what it is today. At the heart of every quasar lies a supermassive black hole, but the relationship between the two is more subtle than it first appears. A black hole by itself is silent. It emits no light, no radiation, no signal that announces its presence. Everything that makes a quasar visible comes from the region just outside the black hole, where gravity is strongest but escape is still possible. This region sits at the boundary between the known universe and the point of no return. It is here that the rules of physics are pushed to their limits, and it is here that quasars become laboratories for extreme relativity. As matter spirals inward toward the black hole, it accelerates to enormous speeds. Close to the center, particles move at a significant fraction of the speed of light. Time slows down. Space becomes curved. The distinction between direction and motion begins to blur. From the perspective of the infalling matter, everything feels normal. But to a distant observer, the processes near the black hole appear distorted. Light loses energy as it climbs out of the gravitational well. Signals slow. Events seem stretched in time. Quasars allow us to observe these relativistic effects directly, not in thought experiments, but in real astronomical data. One of the most striking relativistic features of quasars is how their light behaves. The intense gravity near the black hole bends light paths, warping the appearance of the accretion disk. Light emitted from the far side of the disk can curve around the black hole and reach us, making parts of the disk visible that should be hidden. In some cases, the disk appears brighter on one side than the other, not because of uneven emission, but because of relativistic beaming. Matter moving toward us appears brighter, while matter moving away appears dimmer. These effects confirm Einstein's predictions with remarkable precision. The jets produced by quasars are another direct manifestation of relativity. These jets emerge from the innermost regions near the black hole, guided by powerful magnetic fields twisted by the black hole's rotation. They are narrow, focused streams of particles moving at nearly the speed of light. From Earth, these jets can appear longer than the galaxy that hosts them. In some cases, they extend for millions of light years, carving channels through intergalactic space. The energy carried by these jets is enormous. They can heat entire regions of gas, prevent star formation, and alter the structure of galaxy clusters. What makes these jets even more remarkable is how they appear to violate common sense. When a jet is pointed nearly toward Earth, its motion can appear faster than light. This is not a real violation of physics, but a projection effect caused by relativistic speeds and geometry. The fact that quasars display this behavior tells us just how extreme their environments are. No star, no supernova, no ordinary object can produce such effects. Only the region near a supermassive black hole can. Quasars also give us insight into the nature of black hole spin. Not all black holes rotate at the same rate. Some spin slowly. Others spin near the maximum allowed by physics. This rotation affects how efficiently energy is extracted from infalling matter. Rapidly spinning black holes can produce more powerful jets and brighter quasars. By studying quasar emissions, astronomers can estimate black hole spin, something that cannot be measured directly. In this way, quasars reveal properties of black holes that would otherwise remain hidden. The connection between quasars and black holes also explains why quasars are temporary. A quasar exists only as long as the black hole has access to large amounts of matter. When galaxies merge, gas is driven toward the center, igniting quasar activity. When the fuel supply is exhausted or expelled, the quasar fades. The black hole remains, but the light disappears. This means that quasar activity is closely tied to the violent history of galaxy mergers and interactions. Every quasar we see is evidence of a galaxy in turmoil. As quasars fade, they leave behind clues. The surrounding gas bears scars from powerful winds. Star formation histories show sudden interruptions. The central black hole stands as a massive relic of a once blazing core. By studying these remnants, astronomers can reconstruct the past life of a galaxy. Quasars are not just present-day phenomena. They are historical records written into the structure of the universe. Quasars also challenge our understanding of how black holes grow. Some quasars appear so early in cosmic history that their black holes must have grown at near maximum rates from the very beginning. This raises questions about how the first black holes formed. Did they begin as the remnants of the first massive stars? Did they collapse directly from huge clouds of gas? Or did they form through mechanisms we have not yet discovered? Quasars push these questions into the open. They demand explanations that go beyond slow, gradual growth. Relativity also plays a role in how we detect quasars. Because the universe is expanding, light from distant quasars is stretched to longer wavelengths. This redshift allows astronomers to measure how far away a quasar is and how long its light has traveled. The most distant quasars we observe today come from a time when the universe was less than 1 billion years old. They are among the earliest visible structures ever detected. Through them, we glimpse the universe in its infancy. Despite their distance, quasars remain some of the brightest objects in the sky when viewed with powerful telescopes. This brightness makes them invaluable tools. They allow us to probe conditions in the early universe that would otherwise be inaccessible. They let us test relativity under extreme gravity. They help us measure cosmic expansion. They reveal how matter behaves near the edge of a black hole. In this sense, quasars are not just objects to observe. They are experiments conducted by the universe itself. What makes quasars truly special is that they combine multiple extremes into a single phenomenon. They involve the strongest gravity, the fastest motion, the highest energies, and the largest scales of influence. They compress the drama of cosmic evolution into a single blazing core. Through quasars, we see how black holes are not merely destructive endpoints, but engines that shape the universe on the grandest scales. As our instruments improve, quasars continue to surprise us. New observations reveal complex structures in their accretion disks. Unexpected variations in brightness challenge existing models. Jets show signs of instability and interaction with their surroundings. Each new detail adds depth to our understanding and reminds us that even the brightest objects in the universe still hold mysteries. Quasars stand at the intersection of gravity, motion, energy, and time. They show us relativity in action. They turn invisible black holes into beacons visible across the cosmos. And they reveal that the most powerful forces in the universe are not explosions or collisions, but steady, relentless gravity converting matter into light. Quasars do not burn forever. Despite their immense power, they are temporary phases in the life of a galaxy. This is one of the most important truths about quasars, because it tells us that even the brightest engines in the universe are governed by limits. A quasar shines only as long as it is fed. When the supply of gas and dust around the central black hole begins to change, the quasar begins to weaken. Over time, the blazing core dims, the jets lose strength, and the galaxy settles into a quieter state. What remains is not destruction, but transformation. The fading of a quasar is closely tied to its own power. As the quasar shines, it releases enormous amounts of energy into its surroundings. Radiation pressure pushes outward. Winds driven by intense heat sweep through the galaxy. Jets punch holes through gas clouds and carry matter far away. These processes gradually remove the very fuel the black hole needs to keep shining. In this sense, a quasar helps shut itself down. The more powerful it becomes, the more aggressively it clears its environment. Eventually, there is not enough material left near the center to sustain the accretion disk. The flow of matter slows. The disk cools. The brilliant light fades. This self-regulating behavior explains why quasars do not consume entire galaxies. Without feedback, a black hole might continue growing until it swallowed everything around it. But the energy released by the quasar creates a balance. It limits growth. It prevents runaway collapse. This balance shapes the final structure of the galaxy. It determines how massive the central black hole becomes and how much gas remains available for future star formation. Quasars are not just consumers of matter. They are sculptors. As a quasar fades, its galaxy enters a new phase. Star formation may decline sharply if gas has been expelled or heated. The galaxy may transition from a star-forming spiral into a quieter elliptical shape. Many of the massive elliptical galaxies we see today are believed to be the remnants of intense quasar phases triggered by ancient galaxy mergers. Their smooth shapes and old stellar populations are evidence of a violent past, followed by long stability. The quasar era left its mark not through continued brightness, but through lasting structure. The central black hole remains long after the quasar has shut down. It sits quietly, exerting its gravitational influence, but producing little light. From the outside, the galaxy appears calm, but deep inside, the black hole holds a record of its earlier activity in its mass and spin. By measuring these properties, astronomers can infer how active the galaxy once was. The quiet black holes in today's galaxies are fossils of ancient quasars. This idea changes how we think about galaxies. A galaxy is not just a collection of stars. It is a system shaped by cycles of activity and calm. Quasars represent the most extreme of those cycles. They are short-lived compared to the age of the universe, but their effects last for billions of years. The universe we observe today carries the imprint of countless quasar episodes scattered across cosmic history. Quasars also help explain why the universe looks the way it does on large scales. The distribution of galaxy sizes, shapes, and masses reflects the influence of quasar feedback. Without it, simulations of galaxy formation fail to match observations. Too many massive galaxies form. Too much gas collapses. The universe becomes crowded and chaotic. Quasars restore balance by injecting energy where gravity would otherwise dominate. They act as cosmic regulators, preventing the universe from becoming overly dense and uniform. Even after they fade, quasars continue to influence their surroundings indirectly. Gas expelled during the quasar phase does not disappear. It travels outward, mixing with intergalactic material. Over time, this enriched gas can fall back into galaxies or be incorporated into new ones. The heavy elements created in stars and spread by quasar-driven winds become part of future generations of stars and planets. In this way, quasars participate in the long-term recycling of matter across the universe. The fading of quasars also marks a shift in cosmic time. The universe transitions from an era dominated by violent growth to one defined by gradual evolution. Star formation slows. Galaxy mergers become less frequent. The brightest quasars vanish from the sky. What remains is a quieter universe filled with mature galaxies. This transition tells us that the universe itself evolves, moving through distinct phases just as galaxies do. Yet quasars have not vanished entirely. A small number still shine today, often triggered by recent galaxy interactions. These modern quasars allow astronomers to study the same processes that shaped the early universe, but in closer detail. They act as living laboratories, showing us how quasar activity turns on and off. By comparing ancient and modern quasars, scientists can trace how the conditions for extreme accretion have changed over time. The study of quasar life cycles also reveals something profound about cosmic balance. The universe does not favor endless growth. It favors regulation. Energy flows outward as matter falls inward. Light is produced as gravity tightens its grip. And eventually, the system stabilizes. Quasars embody this balance on the largest scales. They show that even the most extreme phenomena are governed by feedback and limits. Quasars also remind us that brightness can be misleading. A quasar dominates the light of its galaxy, but it does not define the galaxy's entire existence. It is a phase, not a permanent state. This perspective helps us understand why the universe appears calm today despite its violent past. The brightest events were brief. The quiet aftermath is long. As we look at galaxies like the Milky Way, we are likely seeing systems that once blazed as quasars. The silence of our galactic center does not mean nothing happened there. It means something extraordinary happened long ago and has since faded. The calm we experience now is the result of that ancient transformation. Quasars teach us that the universe evolves not through steady uniform change, but through bursts of intensity followed by long periods of stability. They show us that extremes shape outcomes, and they reveal that even the brightest lights eventually dim, leaving behind structures that persist for billions of years. This understanding turns quasars from distant curiosities into essential chapters in the cosmic story. They are not just objects we observe. They are processes that explain why the universe looks the way it does today. Quasars are not only some of the most powerful objects ever formed, they are also some of the most useful, because they shine across enormous distances and remain visible from the farthest reaches of cosmic time. Quasars act as markers embedded throughout the universe. They allow astronomers to measure scale, structure, motion, and evolution in ways no other objects can. In many ways, quasars function like fixed reference points in a universe that is constantly expanding and changing. One of the first things quasars helped scientists understand was the true size of the universe. When astronomers measured the redshift of quasar light, they realized just how far away these objects were. The light had been stretched dramatically by cosmic expansion. This stretching revealed that quasars existed billions of light-years away, meaning their light began its journey when the universe was still very young. Quasars were not just distant, they were ancient. This discovery immediately expanded our sense of cosmic scale. The universe was far larger, older, and more dynamic than previously imagined. Because quasars are so bright, they remain visible even when nearly everything else fades into darkness. This makes them ideal probes of the distant universe. When light from a quasar travels toward Earth, it passes through clouds of gas and dust scattered across intergalactic space. Each cloud absorbs specific wavelengths of light, leaving subtle fingerprints in the quasar's spectrum. By studying these absorption features, astronomers can detect matter that would otherwise be invisible. In this way, quasars allow us to map the universe's hidden structure. These absorption patterns reveal the presence of vast filaments of gas connecting galaxies, as well as enormous voids where little matter exists. Together, these structures form what is known as the cosmic web. Quasars illuminate this web like flashlights shining through fog. Without them, much of the universe's large-scale structure would remain undetectable. Quasars show us that matter is not randomly scattered, but organized into an intricate network shaped by gravity over billions of years. Quasars also help scientists study how the chemical makeup of the universe has changed over time. Early in cosmic history, the universe contained mostly hydrogen and helium. Heavier elements formed later inside stars and were spread by explosions and winds. As quasar light passes through gas clouds at different distances, it reveals the chemical composition of those clouds at different moments in time. This allows astronomers to trace how elements like carbon, oxygen, and iron gradually spread across the cosmos. Quasars become time machines, letting us watch the universe grow more complex as generations of stars live and die. Another crucial role quasars play is in measuring cosmic expansion. The universe is expanding, and the farther away an object is, the faster it appears to be moving away from us. Quasars, because they are visible at extreme distances, extend this measurement far beyond nearby galaxies. By comparing quasar redshifts across different regions of the sky, astronomers can study how expansion has changed over time. This helps refine models of dark energy, the mysterious force driving the accelerated expansion of the universe. Quasars are also used to test fundamental physics. Because their light travels such vast distances, even tiny effects can accumulate over time. If the laws of physics were different in the past, Quasar light might reveal those differences. Scientists study quasar spectra to look for variations in physical constants, changes in particle behavior, or signs of new physics. So far, the universe appears remarkably consistent. The same rules apply billions of years ago as they do today. Quasars help confirm this stability. In some cases, quasars also serve as natural gravitational experiments. When a massive object lies between Earth and a distant quasar, its gravity bends the quasar's light. This effect, known as gravitational lensing, can split a single quasar into multiple images or stretch it into arcs. By studying these distortions, astronomers can measure the mass of the intervening object, including dark matter that emits no light. Quasar lensing allows scientists to map invisible mass and test predictions of general relativity on cosmic scales. Quasars also help measure distances in a universe where distance is difficult to define. Unlike nearby stars, we cannot measure quasar distances using simple geometry. Instead, scientists rely on their brightness, redshift, and variability. While quasars are not perfect standard candles, their behavior still provides valuable constraints on cosmic distances. Combined with other measurements, they help anchor the cosmic distance ladder, connecting nearby observations to the farthest reaches of space. Another powerful use of quasars is in studying the epoch when the universe transitioned from darkness to light. After the Big Bang, the universe cooled and became filled with neutral hydrogen that blocked light. Quasars helped end this darkness. Their intense radiation ionized surrounding gas, making the universe transparent. By observing quasars at different distances, astronomers can pinpoint when this transformation occurred. Quasars mark the moment when the universe became visible on large scales. What makes all of this remarkable is that quasars were not designed to be tools. They are simply natural outcomes of gravity operating under extreme conditions. Yet their brightness and reach turn them into some of the most powerful instruments in astronomy. They allow us to study regions we cannot otherwise access. They provide information about matter, energy, time, and space across billions of years. Even today, new quasar surveys continue to reshape our understanding of the universe. Each newly discovered quasar extends the boundary of what we can observe. Each new spectrum adds detail to the cosmic map. Each new measurement refines our models of how the universe works. Quasars remain essential not because they are rare curiosities, but because they connect so many aspects of cosmic science into a single phenomenon. Through quasars, we measure distance without traveling, time without clocks, and structure without touching matter. They show us the universe not as it is now, but as it was across nearly its entire history. They turn light into information and distance into knowledge. In this way, quasars are not just objects in space. They are bridges between observation and understanding. They allow us to transform faint photons into a detailed picture of the universe's past, present, and future. Even after decades of study, quasars continue to surprise astronomers. Just when the basic picture seems clear, a supermassive black hole, a glowing accretion disk, powerful jets, the universe presents examples that do not fit neatly into expectations. These strange quasars are not mistakes or anomalies to be ignored. They are signals that our understanding is still incomplete. They show us where current theories bend, stretch, or fail, and they point toward deeper layers of physics still waiting to be uncovered. Some quasars appear far brighter than they should be given their estimated black hole mass. According to standard models, there is a limit to how much light a black hole can produce before radiation pressure pushes infalling matter away. This balance is known as the Eddington limit. Yet some quasars seem to exceed it. They shine so intensely that, by existing at all, they challenge the idea that black hole growth must be slow and regulated. These objects suggest that under certain conditions, matter can fall inward faster than radiation can push it away. If true, this would help explain how enormous black holes formed so early in the universe. It would mean that gravity sometimes wins completely, overwhelming the mechanisms meant to restrain it. Other quasars behave in ways that seem to contradict their surroundings. Some are found in galaxies that appear relatively undisturbed, without the clear signs of recent mergers that are often thought to trigger quasar activity. This raises an important question. If galaxy collisions are not always responsible for feeding black holes, what else can deliver vast amounts of gas to the center? Perhaps slow internal processes can funnel material inward over long periods. Perhaps early galaxies were structured differently, allowing gas to fall toward the core more easily. Or perhaps there are feeding mechanisms we have not yet identified. These quasars remind us that the universe rarely follows a single rule. There are also quasars that seem to flicker on and off over surprisingly short timescales. Some change their appearance dramatically within years or even months. They transition from bright quasar states to much dimmer ones, and then sometimes brighten again. These so-called changing-look quasars challenge the idea that quasar phases last for tens of millions of years without interruption. Instead, they suggest that accretion can be unstable, turning on and off as gas flows fluctuate. The environment around a black hole may be far more dynamic than once believed, responding quickly to changes in magnetic fields, disk structure, or incoming material. Some of the strangest quasars are those with unusually weak emission lines. In most quasars, gas clouds surrounding the accretion disk glow brightly when energized by intense radiation. These clouds produce distinct spectral lines that help astronomers identify quasars and study their properties. But some quasars lack these features. Their spectra are nearly featureless, making them difficult to classify. This raises questions about whether these quasars are missing entire regions of gas, or whether their radiation is somehow suppressing line formation. These objects blur the line between quasars and other active galactic nuclei, suggesting a continuum rather than clear categories. Then there are quasars with jets that appear misaligned or asymmetric. In many systems, jets shoot out in opposite directions, aligned with the black hole's rotation axis. But some quasars show jets that bend, twist, or even change direction over time. This could be caused by interactions with surrounding gas, changes in black hole spin, or precession of the accretion disk. These distorted jets tell us that the space around a black hole is not a calm, stable environment. It is turbulent, shaped by competing forces acting over enormous scales. Perhaps the most puzzling quasars are those that seem to exist too early. Astronomers have discovered quasars whose light began traveling toward us when the universe was less than 1 billion years old, yet their black holes already weighed billions of times the mass of the Sun. According to standard growth rates, there simply should not have been enough time for them to form. These early quasars force scientists to rethink how the first black holes were born. They suggest that the seeds of supermassive black holes may have been much larger than previously assumed, or that early growth was far more efficient. These objects push the boundaries of what we believe is possible under known physics. Some quasars also exhibit extreme winds, moving at significant fractions of the speed of light. These winds carry enormous amounts of mass and energy away from the black hole. They are capable of stripping gas from the host galaxy and shutting down star formation almost completely. Observations of these winds show that they are not smooth or uniform. They are clumpy, variable, and unpredictable. This complexity suggests that quasar feedback is not a simple process. It is chaotic, shaped by magnetic fields, radiation pressure, and the detailed structure of the accretion disk. There are even quasars that appear to be gravitationally lensed in complex ways, producing multiple images that vary independently. These systems allow astronomers to probe not only the quasar itself, but also the distribution of matter between the quasar and Earth. Small differences in brightness between the images can reveal the presence of stars, planets, or dark matter clumps in the lensing galaxy. In this way, strange quasars become tools for studying structure on scales far smaller than we could otherwise observe. Each of these unusual quasars forces scientists to ask deeper questions. Are our models too simple? Are we missing key physical processes? Do black holes behave differently under extreme conditions than our theories predict? The answers are not yet clear. What is clear is that quasars are not a uniform population. They are diverse, dynamic, and sometimes unpredictable. This diversity is not a weakness in our understanding. It is a guide. It tells us where to look next. The strangest quasars remind us that the universe does not exist to satisfy our expectations. It operates according to its own rules, revealing them slowly through observation and experiment. Every time a quasar defies prediction, it offers an opportunity to refine our theories. It pushes astrophysics forward by exposing gaps in our knowledge. In this sense, quasars are not just objects to be explained. They are teachers. They show us where gravity becomes dominant, where energy reshapes matter, and where time itself behaves differently. They reveal the complexity hidden behind even the brightest points of light. And they remind us that the universe is still full of surprises, even in phenomena we think we understand well. As technology improves and new observatories come online, astronomers will discover more quasars, including ones unlike anything we have seen before. Each new discovery will add another piece to the puzzle, deepening our understanding of how the universe works at its most extreme limits. Quasars are not finished telling their story. And as long as they continue to challenge our theories, they will remain one of the most important keys to understanding the cosmos. Quasars are often described as ancient objects, relics of a violent early universe, but their importance doesn't end in the past. To truly understand quasars, we must also understand what they mean for the long future of galaxies and the universe itself. Quasars are not just episodes of extreme brightness. They are turning points. They represent moments when galaxies are fundamentally changed, redirected onto new evolutionary paths that last for billions of years. When a quasar shuts down, the galaxy it leaves behind is not the same galaxy that existed before the quasar ignited. The intense radiation, winds, and jets released during the quasar phase permanently alter the distribution of matter. Gas that once cooled and collapsed into stars may be gone forever, expelled into intergalactic space. In many cases, this marks the end of major star formation. The galaxy enters a long, quiet phase dominated by aging stars. This is why many massive galaxies today are filled with old, red stars and show little sign of new stellar birth. Their quasar phase effectively ended their ability to renew themselves. This process means quasars play a direct role in shaping the future appearance of the universe. Without quasar activity, galaxies would continue forming stars for much longer. The universe would be brighter, bluer, and far more crowded with massive gas-rich systems. Instead, quasars helped bring balance. They prevented runaway growth. They ensured that galaxies reached a stable form and then settled into cosmic maturity. In this way, quasars helped determine not just how galaxies look, but how long they remain active. The influence of quasars also extends beyond individual galaxies. The energy they inject into surrounding space affects entire galaxy groups and clusters. Jets from quasars can heat enormous regions of gas between galaxies, preventing that gas from cooling and collapsing. This slows the formation of new galaxies and alters the structure of galaxy clusters. Over time, this feedback shapes the large-scale organization of matter in the universe. The cosmic web itself carries the imprint of ancient quasar activity. As the universe continues to age, quasars become increasingly rare. The expansion of space pulls galaxies farther apart. Gas becomes more diffuse. Galaxy mergers become less frequent. Without mergers to drive gas inward, black holes struggle to find enough fuel to ignite quasar-level activity. The era of quasars fades as the universe enters a quieter, more stable phase. This decline is not sudden. It is gradual, unfolding over billions of years. But the trend is clear. The brightest engines of the cosmos belong to the past. Yet even in a future universe with few or no quasars, their legacy remains. Every massive galaxy carries a supermassive black hole. At its center, a silent reminder of a time when that core once blazed with quasar light. These black holes continue to influence their galaxies gravitationally. They shape stellar orbits. They anchor galactic centers. And under the right conditions, they can awaken again, briefly rekindling quasar-like activity. This possibility means quasars are not entirely finished. They are dormant rather than extinct. Given enough time and the right circumstances, galaxies can still experience renewed activity. A merger, a close encounter, or a sudden inflow of gas can reignite the central black hole. The universe may never return to the quasar-dominated era of its youth, but localized bursts of quasar activity can still occur far into the future. Looking even farther ahead, quasars raise deep questions about the ultimate fate of matter and energy. Supermassive black holes continue to grow slowly over time, even in quiet galaxies. They accumulate mass through occasional accretion events and mergers with other black holes. Over trillions of years, black holes may become the dominant repositories of matter in the universe. In such a future, quasars represent the peak moments of energy release before darkness gradually takes over. In this sense, quasars are cosmic milestones. They mark the universe's transition from creation to consolidation. They are the brightest expressions of gravitational energy, appearing at a time when matter was abundant and structures were still forming. As the universe ages, those conditions disappear. Quasars fade not because they are fragile, but because the universe itself changes. Quasars also offer insight into how complexity arises and declines on cosmic scales. They show that complexity does not grow forever. It reaches a peak and then stabilizes or declines. The early universe was simple, hot, and uniform. The quasar era was complex, energetic, and chaotic. The modern universe is structured but calmer. This arc of change suggests that the universe has a life cycle, moving through phases just as stars and galaxies do. From a broader perspective, quasars help us understand our place in cosmic time. We exist long after the peak of quasar activity. The universe around us is quieter and more stable because of what quasars did billions of years ago. The fact that galaxies like the Milky Way are relatively calm today may be a direct result of ancient quasar feedback that shaped their evolution early on. Quasars also remind us that the universe is not designed for permanence. Even the brightest objects fade. Even the most powerful engines shut down. What remains is not emptiness, but structure shaped by past intensity. This pattern appears everywhere in nature, from stars to galaxies to the universe itself. Quasars are simply the most dramatic example of this principle on the largest scales. As we look forward in time, quasars stand as monuments to what the universe is capable of under the right conditions. They represent the upper limit of steady energy production. They show us what happens when gravity, motion, and matter align perfectly. And they offer a glimpse of a universe that once burned far brighter than it does today. Understanding quasars is not just about understanding the past. It is about understanding the trajectory of cosmic evolution. It is about seeing how extremes shape outcomes, how balance emerges from chaos, and how the universe moves from intensity toward quiet stability. Quasars may no longer dominate the sky, but their influence is woven into everything we see. The galaxies around us, the structure of cosmic space, and even the conditions that allow stars and planets to exist all carry the imprint of ancient quasar light. When we step back from the details and look at quasars as a whole, their deeper importance becomes clear. Quasars are not just extreme objects. They are messages from the universe about how reality behaves under the most intense conditions allowed by physics. They show us what happens when gravity is pushed to its limits, when matter is accelerated to near the speed of light, and when energy is released on scales that dwarf anything else we observe. In doing so, quasars reveal fundamental truths about space, time, and the structure of the cosmos itself. One of the most important lessons quasars teach us is that gravity is not a gentle force. In everyday life, gravity feels weak. It keeps our feet on the ground and planets in their orbits, but it rarely feels dramatic. Quasars reveal gravity's true nature. Near a supermassive black hole, gravity becomes the dominant force in existence. It controls motion, bends light, slows time, and converts matter directly into energy. Quasars are gravity operating without restraint. They show us that gravity is capable of producing more power than any nuclear reaction, more influence than any explosion, and more transformation than any other known process. Quasars also demonstrate that light itself is deeply connected to gravity. The light we see from a quasar carries information about warped space, stretched time, and extreme motion. It is not just illumination, it is evidence. Every photon escaping a quasar's core has climbed out of a deep gravitational well. In doing so, it loses energy, shifts in wavelength, and carries the imprint of relativity. By studying quasar light, we are effectively reading the shape of space-time written into radiation. This makes quasars some of the clearest confirmations of Einstein's ideas on the largest possible scales. Another profound insight from quasars is the idea that the universe is shaped by feedback rather than simple accumulation. It is tempting to imagine cosmic evolution as a one-way process where matter simply gathers under gravity and structures grow larger over time. Quasars show us that growth is always balanced by resistance. As black holes grow, they release energy that pushes back. As galaxies accumulate gas, quasars heat and expel it. This feedback prevents unchecked collapse and runaway growth. It creates balance. Without this balancing mechanism, the universe would look nothing like it does today. Quasars also force us to rethink the idea of isolation in the universe. Although they originate in compact regions, their influence extends far beyond their host galaxies. A single quasar can affect regions millions of light-years away. It can alter gas between galaxies, influence future star formation, and reshape large-scale cosmic environments. This shows us that nothing in the universe exists in isolation. Every extreme event has consequences that ripple outward through space and time. The existence of quasars also reveals something about the early universe that would otherwise remain hidden. Their presence tells us that massive structures formed quickly. The universe did not evolve slowly and gently from simplicity to complexity. Instead, it passed through a phase of rapid growth, intense energy release, and dramatic transformation. Quasars mark that phase clearly. They are signposts indicating where and when the universe reached peak intensity. Quasars also blur the line between order and chaos. On one hand, they arise from predictable physical laws. Gravity pulls matter inward. Motion generates heat. Magnetic fields channel energy. On the other hand, the environment around a quasar is turbulent, unstable, and unpredictable. Accretion disks fluctuate, jets wobble, emission varies. This combination of strict laws and chaotic behavior reflects a deeper truth about the universe. Order and disorder coexist. The universe is governed by rules, but those rules allow complexity to emerge naturally. There is also a philosophical dimension to what quasars represent. They remind us that the brightest objects are often fueled by destruction. A quasar shines because matter is being torn apart, heated, and lost forever beyond an event horizon. Light is produced at the edge of disappearance. This paradox runs throughout the universe. Stars shine by consuming fuel. Galaxies grow by merging and disrupting one another. Even life exists by consuming energy. Quasars are simply the most extreme expression of this universal pattern. Quasars further challenge our intuition about scale. From Earth, a quasar appears as a tiny point of light, often indistinguishable from a star. Yet that point represents an energy output greater than an entire galaxy. This disconnect between appearance and reality is a recurring theme in cosmology. The universe is filled with structures that hide their true nature behind misleading simplicity. Quasars teach us to question appearances and rely on deeper understanding. They also remind us that the universe is not static. Everything changes. Even the most powerful objects evolve, fade, and transform. Quasars do not represent a permanent state. They represent moments, intense, short-lived moments that leave long-lasting consequences. This idea applies across all scales, from stars to galaxies to the universe itself. Change is the rule, not the exception. In a broader sense, quasars show us how much of the universe operates beyond direct human experience. The conditions near a quasar are so extreme that they cannot be replicated on Earth. Temperatures, densities, and energies reach levels that exist nowhere else. Yet through observation and theory, we can still understand them. Quasars demonstrate the power of science to reach far beyond the limits of our senses and reconstruct realities we will never visit. Quasars also raise questions that remain unanswered. How exactly did the first supermassive black holes form? Why did some galaxies produce quasars while others did not? How do accretion disks remain stable under such extreme conditions? Are there limits to how bright a quasar can be? Or do we simply not yet understand the extremes? These questions keep quasars at the center of modern astrophysics. Perhaps most importantly, quasars remind us that the universe is capable of producing phenomena far beyond what seems reasonable. If quasars did not exist, we might assume that black holes are quiet, distant curiosities. Instead, quasars show us that black holes can dominate cosmic history, reshape galaxies, and illuminate the universe across billions of light years. They expand our sense of what is possible. As we approach the end of this journey, it becomes clear that quasars are not just objects to be catalogued. They are windows into the deepest workings of reality. They connect gravity to light, matter to energy, and the past to the present. They show us the universe at its most intense and most revealing. Quasars are the universe speaking at maximum volume, telling us how it grows, how it balances itself, and how it transforms over time. And by listening carefully to that light, we learn not only about distant galaxies, but about the fundamental nature of existence itself. When we look at quasars as a complete phenomenon, they stop being just objects in space and start becoming milestones in the history of the universe. They mark moments when the universe pushed its own limits, when gravity gathered matter so efficiently that light itself became overwhelming. Quasars are not accidents. They are outcomes. They exist because the universe allows matter, motion, and space-time to combine in ways that produce extraordinary results. In that sense, quasars are not strange. They are inevitable. Every quasar represents a brief but intense chapter in the life of a galaxy. Before the quasar ignites, the galaxy is rich in gas and chaos. During the quasar phase, energy dominates, matter is reshaped, and the future of the galaxy is decided. After the quasar fades, what remains is a quieter, more stable system, carrying the imprint of that earlier violence. This pattern repeats across the universe. Galaxies are not born calm. They are forged through extremes, and quasars are among the most extreme expressions of that process. Quasars also reveal how deeply connected the universe is across time. When we observe a distant quasar, we are not just seeing a faraway object. We are witnessing an era when the universe itself behaved differently. The laws of physics were the same, but the conditions were not. Matter was more abundant. Distances were smaller. Interactions were more frequent. Quasars are messengers from that era, carrying information that no nearby object can provide. They allow us to study a universe that no longer exists in the same form. In doing so, quasars give us perspective. They show that the calm night sky we see today is the result of ancient turmoil. The stable galaxies around us are survivors of a violent youth. Even the conditions that allow stars, planets, and life to exist may depend on quasar activity that regulated growth and prevented chaos from continuing unchecked. In a very real sense, quasars helped prepare the universe for complexity, including the possibility of observers who could one day study them. Quasars also stand as reminders of the power hidden inside gravity. Gravity is often described as the weakest force, yet quasars show that when gravity operates over enormous masses and distances, it becomes unmatched. It can outshine galaxies. It can reshape cosmic environments. It can dominate the evolution of the universe. Quasars reveal gravity not as a passive background force, but as an engine capable of extraordinary transformation. There is also a humbling lesson in quasars. They demonstrate that the most dramatic events in the universe are not explosions that destroy everything in an instant, but sustained processes that operate over millions of years. A quasar shines steadily, relentlessly, reshaping its surroundings through constant energy release. This quiet persistence is more influential than sudden violence. It shows that change in the universe often comes from endurance rather than shock. As our technology improves, quasars will continue to play a central role in astronomy. New telescopes will detect even fainter and more distant quasars. More detailed observations will reveal finer structures in accretion disks and jets. Subtle variations in quasar light will test our understanding of relativity, magnetism, and quantum processes. Each new observation will refine our picture of how these extraordinary objects work. Quasars are not relics of a finished story. They are active participants in ongoing discovery. Yet even with all we have learned, quasars remain partially mysterious. We still do not fully understand how the first supermassive black holes formed. We still struggle to explain the most extreme examples. We still refine our models to account for unexpected behavior. This is not a weakness of science. It is a sign that quasars sit at the edge of our understanding, where progress is still being made. In the end, quasars remind us why we study the universe at all. They show us that reality is richer, more intense, and more surprising than intuition suggests. They demonstrate that simple laws can produce astonishing complexity. And they prove that even from billions of light years away, the universe can still speak to us through light. A quasar is not just a distant beacon. It is a record of gravity at its peak, a witness to the universe's most active era, and a guide to understanding how cosmic structure emerged. By studying quasars, we are not just learning about black holes or galaxies. We are learning how the universe builds itself, regulates itself, and evolves over time. The light from a quasar may have traveled for billions of years to reach us, but the story it tells is immediate and clear. The universe is capable of extremes. It grows through intensity, and even in its brightest moments, it is shaping a future far quieter than its past. That is what quasars truly are, not just the brightest objects ever seen, but milestones in the long journey of the universe itself. Quasars show us the universe at its most intense, when gravity turns matter into light and galaxies are reshaped from the inside out. They remind us that the calm cosmos we see today was once violent, brilliant, and full of transformation. Every quasar is a message from that distant era, carrying the story of how the universe grew, balanced itself, and slowly became what it is now.